And so the final part of today, we're really going to finish off the transduction mechanisms, and I'll show you at the end just a few of the MEMS devices we actually make in Glasgow. So this is just really following on, giving a bit more detail about some of these transduction mechanisms that are used in real vibrational energy harvesters. So the first one is going back to the electromagnetic. So really what we have here is the coil and a magnet, and we're using the Faraday induction. So either a moving coil or a moving magnet, one through the other, allows us to generate an electrical current in the coil. And this is what we showed in the second lecture. Here's some examples of microfabricated, where there's permanent magnets on a silicon paddle. So this is our proof mass that moves around, and the coil gets wrapped around this. Here's the actual microfabricated device. You can see the magnet actually the whole way across. And this is an example of a microfabricated copper coil to actually produce the coil that you can see here. Now, there's different ways people have used these systems. So this is one example of taking a silicon nitride membrane with a silicon mass, having a silicon wafer with gold coils fabricated in the bottom. And this is easy to mass produce at wafer scale in MEMS foundries. And you wafer bond these pieces together, giving you the vibration with the coil. So the advantage of electromagnetic is that the physics is very well understood. You don't need any source voltage to actually start the electricity generation. Now, you'll see when we go to some of the other techniques, one of the problems is you need to apply a voltage to be able to generate electricity, which means you need a battery or you need a source of electricity to start with. The disadvantages, well, there's a perpetuum use electromagnetic, but you're limited with the winding turns in MEMS, so you end up in all the systems having very low voltage. Now, with modern electronics down at 0.5 volt, that certainly these systems can be used, but the perpetuum system is not MEMS. It's actually quite a big, it's a coffee cup size, 15 cubic centimeter system. So when you scale this down to the wafer scale, the powers go down and it's less efficient. You get low damping forces and low frequency operation. So these systems, as they're normally set up, the transduction efficiency is extremely low. So as stated before, these sorts of systems are about 0.1% efficient in taking the vibrational energy and converting that to electricity. If we look at the electrostatic, so this is where we actually have to have an input voltage. As the proof mass with the interdigitated fingers compared to the side, we get a voltage being created, and the energy that's available relates to the change in capacitance. So just as the distance between these fingers changes, we have a change in the capacitance. So we go between a maximum and a minimum value, and the V max is the maximum voltage we have across this switch that's here. Now here's an experimental one that you can see the fingers and they overlap by about 250 microns. The disadvantage of these systems is you can only have very low displacements. So here, in fact, we're talking about displacements of order of 20 microns. So if there are certain vibration systems where the amplitudes will be much higher than this, and then these particular electrostatic transduction mechanisms are not appropriate to use. So the advantage is this can be done very easily in silicon at extremely low cost using MEMS and mass manufacture. In fact, the gyroscope that's in your mobile phone uses these sorts of interdigitated fingers and this capacitance readout mechanism to measure the displacements in different directions. So that's what determines which way the screen on your mobile phone is pointing. The big disadvantage is you need an input voltage. So that's fine if you have a battery or you have power available, but otherwise you need some sort of external power source, and that's not always available for every application you might look at. High output voltages require transforming. Well, one of the advantages here is that the output voltage is high, partly because you also need this input voltage. For many of the applications, we're talking about tens of volts here. And for consumer electronics and also for health and safety, those things are actually not that useful in some environments. So this is one of the reasons electrostatic is not used for many applications. So piezoelectric, well, as I stated earlier, piezoelectric is where, as the material displaces, you end up with a voltage being generated. And what's actually happening is that you have different atoms in the crystal that, as the crystal changes, some of the atoms move and other atoms don't. So here's an example where as the material gets displaced, you actually have one of the atoms remaining in the same place while the rest of the crystal displaces completely. And that, if it's got a positive charge or a negative charge, ends up creating a voltage, and you can extract the energy out of this. So the big advantage of these systems is that you get a voltage and a current generated simply due to the movement of the polarized charge in the piezoelectric material. The disadvantage you have is that that typically is a fairly small effect in most of the piezoelectric materials that certainly have been used to date. So to show how this might work, and this is a real example out of the literature in a publication. So lead, zinc, tellurium, PZT has got one of the highest piezoelectric coefficients. Here's applying a force vertically to, in fact, it's a silicon membrane on top of a silicon wafer. They've put PZT deposited, and they've got just a mass has been put on the top. This is using SU8 resist. Don't worry too much about that, it's just a mass going on top. They then have interdigitated electrodes that, as the PZT is bent, so the proof mass goes up and down, the forces here change the amount of voltage, and from that you can generate a current. So the advantages that you have is, even at the very low frequencies, where some of the other systems don't work, actually piezoelectrics are much more efficient at electricity conversion, particularly at the lower frequencies that electromagnetic and electrostatic don't work very well. It works with very simple geometries compared to some of the other systems. But again, it's got low coupling coefficients, there's poor extraction efficiency. The other thing is that almost all piezoelectric materials use toxic or dangerous materials, and they're typically very difficult to integrate into MEMS foundries and mass manufacture cheaply and safely. So actually, with vibrational systems, there isn't a perfect transduction mechanism that works for all applications. So let's compare some technologies. Now, I've deliberately put up this slide. It comes from a review article by Steve Beebe down at the University of Southampton. And what he's actually showing in this is a comparison between many research papers published in the literature on vibrational energy harvesters. So there's electromagnetic, there's piezo electric, there's some electrostatic generators, and every single one has picked a different resonant frequency to measure, with a different acceleration, with different masses. And all of them claim they have great performance. So what Steve Beebe has done is try to get a figure of merit that he calls the normalized power density to try and make a direct comparison between all these different techniques. So what he's plotted is this normalized power density, and that's the electrical output power that they each generate. So that's the value that you see here. So you see most of these are microwatts. There's a few, the perpetuum one here, that's 4 milliwatts. But then you divide by the mass of your proof mass and the acceleration that we have here. Now, when you put these all together and you compare between volume, you can see that you get a whole series of distributions. So the best you can be is up this corner. You want to be as high up to the left as you possibly can. But you typically have got a relationship that actually runs in this direction. So the larger the volume of your system, the easier it is to get much higher electrical power compared to the proof mass of your system. So you can see the very small systems, you actually end up having very low powers. And the real problem in how this is shown, we spoke earlier about, we have an omega cubed here for the available power. But actually, this is an academic taking a very unrealistic frequency, because the majority of applications are all below 200 hertz, excuse me, and many of them are below 100 hertz. So, for instance, the automotive and the train vibrational monitoring, that typically is around 50 to 60 hertz is where the maximum in the power is available. So hence the lower frequencies are really where the applications sit. Now, this is a field that there's still an enormous amount of research going on, both in universities and some research definitely going on in different companies in this space. Now, I've shown you typical systems that are out there. Some of the real problems is that at the moment, all the commercial systems really only vibrate in one dimension. And what I mean by that is that they're only extracting energy from vibrating systems that go up and down or travel in 1D. There are many examples where, in fact, you could potentially improve the amount of energy you can extract if you could extract in multiple directions. This is one example out of a paper from about 8 years ago that shows a particular spring to try and have rotational energy come out of a particular system. There's also been gyroscopic designs, but the real problem I spoke about earlier, and one of the problems why vibrational energy harvesters are not much more ubiquitous and used for many more applications, is that they're typically designed to be quite wide bandwidth, so they have a lot of applications with the resonant frequencies. That gives you, unfortunately, a very low vibrational to electricity transduction coupling mechanism. And there are examples where people have spoken about going to resonant frequencies. That gives you much smaller bandwidth that the system will work in terms of the frequency response, but your ability to generate electricity increases in efficiency quite significantly. So there's a lot to do in this space. There's a lot of people doing research in this space. It's something that will develop. And many of these early systems are already out there, actually not using battery power, extracting energy out of waste or out of vibrational motions. Powers are still quite small, but there's still a lot of potential research that can be done here to improve these thermoelectric and vibrational energy systems. So for some of you, that might be an area that doing a PhD or going on to a details research master or go and work in a company that works in this may be of interest to you. Well, that's the formal teaching for today over. I've gone through thermal energy harvesting using thermoelectric generation and demonstrated it typically has very low efficiency. Heat is ubiquitous and waste heat is plentiful. So the big advantage of those thermoelectric systems is that you're getting the fuel or the energy for free, if you like. The other big advantage we spoke about is they really are fit and forget solutions that you can put them in and not have to worry about them, certainly for many decades. In reality, though, thermoelectrics for heat pumps, particularly for telecoms lasers, is the biggest application at the moment. And there's other areas where Peltier and thermoelectric heat pumps are used. The second half, we spoke about the vibrational energy harvesters and how they can be used to generate powers at resonant frequencies. But the bandwidth of operation is poor on present vibrational harvesters, and the conversion efficiencies are extremely low. But what we're talking about here is a whole market around self-powered autonomous sensors, where you don't have to have wires in a car to a sensor that might be in a corner of a car or in an aircraft, where you have wireless communications, and you don't have to have any wires for power or any batteries in the system that might run out or have to be replaced over time. So this is an area in terms of sustainable energy that is increasing the whole time. And while it might be tiny compared to what goes on with what we spoke about with hydro and with photovoltaic and some of the other schemes, this is already over $10 billion per annum market. Right, for a bit of fun for the last couple of minutes, I just thought I'd show you some of the other research that I'm certainly involved in Glasgow. One of the things we've done with MEMS devices, and this is a real mass in a spring that we made out of silicon. You can see here the proof frame, you can see the mass. We have 4 springs. Well, these are actually anti-springs. And what we did is we made something that, rather than the Hooke's law, that the spring constant or the spring gives you a bigger retaining force as you load it. This actually gets softer the more we load it with the proof mass. Now, what we've done with it is that we've measured gravitational attraction. And all we're talking about here is Newton's law of gravity. So if we have a big mass and a small mass, Newton said we've got a force between the two, and that force is given by big G, the gravitational constant, times the large mass, times the small mass, times the distance between the two masses squared. Now, what we use this little proof mass, this is 0.14 of a milligram, because it's made out of silicon. It's only about 12 millimeters in size. It's the same technology in your mobile phone for the accelerometers and the gyroscopes. We then measured the proof mass going up and down, and we managed to measure the gravitational force of the moon going around the Earth. So this red line is theoretically the force that we should see in Glasgow for the moon going around the Earth, and our MEMS proof mass went up and down to this blue curve that corresponded to us being able to measure the gravitational attraction of the moon. Now, the moon is a long way away. This same device could actually measure the gravitational attraction of a person about 1 meter away. And it gives you an idea that this is measuring gravity down to parts per billion. Now, we started this research with a lab, a rack of equipment, a big vacuum chamber to give it thermal isolation to the outside world. We then miniaturized this. We've gone and done field trials, gravity sensing. This is used for oil and gas detection, but also it's used for a whole series of other applications, such as detecting sinkholes. And we've now scaled this down so it can go into a little vacuum package for MEMS devices. We actually went up the Campsie Fells, just north of Glasgow, and we measured it at car park at the bottom. We then went up the top, and as we move away from the Earth's surface, we have what's known as the free air effect, and the gravity signal decreases. But it didn't decrease as much as we expected from just moving away from the center of the Earth by 270 meters. And that's because, in fact, the Campsie Fells, as geologists in Glasgow showed 200 years ago, are made out of granite rock. So the additional density we can measure, and that's called the Bouguer effect. So this is why geologists use gravimeters. You can actually measure the density with them and understand the different geological strata under the ground. Well, this is what one of these devices now looks like. You can see it really is a mass in a spring. And as we excite it with a pair of tweezers, you can see the mass moving up and down in the springs. Now, in fact, we've improved this. We've now been able to see, this is the moon. This little dip here is actually the gravitational force in the sun. And you can see that over now, we've gone up to 19 days measuring it. Well, what are we wanting to do with these sensors? Well, in fact, one of those sensors has already gone to Mount Etna. And what we're trying to do is a whole array of these gravity sensors on the side of Mount Etna, and then try and see if we can image the magma moving around under the volcano. And can we actually determine when the volcano is about to erupt? So this is a European project that we're working with a whole load of geophysicists in Italy, in the Netherlands, in Germany, and also with a French company that builds quantum gravimeters. We're putting our 30 MEMS devices with a quantum gravimeter on Mount Etna, and we're trying to see if we can determine when the volcano may next erupt. So that's been delayed a bit from COVID, but we're presently trying to get those sensors onto Mount Etna. Right, I'm going to stop the recording for today.